Okay, so we have Laura Donnay giving a review about flat space holography. Yeah, thanks.
Thank you. I hope you can hear me. I want to start by thanking, of course, the organizers for putting together this wonderful conference and for the invitation to give this review talk today. So it's going to be a review talk about flat space holography. Let me start by saying that in the absence of such a holographic correspondent for flat spacetimes, I will not be able to tell you what exactly flat space holography is, or how it works, or what you should do, but rather I want to present recent advances in these programs and what I think are promising paths towards making such a holographic principle for asymptotic flat spacetime concrete. So I want to say that I'm happy to take questions during, so please feel free to interrupt me, shout, and I can repeat the questions if something comes up to your mind. I prefer this than speaking all the way for 15 minutes. So the motivation for this question is pretty simple. We would like to understand how the holographic principle carries along for realistic spacetimes. By that I mean four-dimensional asymptotic flat spacetime, so which have vanishing cosmological constant. Of course, these spacetime have a huge range of application from collider physics to astrophysical scales, provided, of course, you stay beyond cosmological scales, where, of course, we know that we live in a universe with a positive cosmological constant. In particular, one of the reasons why we expect that there should be a holographic principle at play here is given by this beautiful Bekenstein-Hawking formula for black hole entropy, which is saying that the entropy of the area of the black hole scaled with the area rather than the volume. And, this formula is also true, doesn't only works in certain space-time, certain dimension, it's rather universal and also hold for black holes at the center of our galaxy. So that's the main purpose of this program, is to try to see whether we can extend some of the aspects of holography beyond the canonical cases that is known to work in a beautiful way in the context of the ADS-CFT correspondence. So this is not a new question. This after Maldacena seminal paper on holography, there has been early attempts to address this question. I'm just listing a few from different perspectives. And in fact, even earlier, even before holography was formulated, it was a sort of a program of Newman and Penrose to try to aim at a reconstruction of the quantities in bulk, Minkowski, from quantities defined solely at the boundary, at null infinity. So we may wonder why coming with such a correspondence is so hard and has not been achieved. And I want to point out some of what I think are the main difficulties for such a thing, or what you might consider as some obstructions for this. So it all can be traced back when you can get the Penrose diagram for flat spacetime. So as you can see here, the conformal boundary of Minkowski space includes several disconnected pieces. You have future and past time-like infinities. This is the location where massive particles enter spacetime and exit spacetime. You also have future and past null infinities, where massless particles enter and exit spacetime. And as some sort of a junction, looking like a point in this Penrose diagram, you have a spatial infinity. So you have all these different boundaries that you have to account for. And this is in contrast with ADS case, where we have a nice time-like Lorentzian boundary. Moreover, if you want to describe realistic phenomena happening in flat spacetime, you better account for fluxes of radiation going through the spacetime. We take the opposite, usually the opposite point of view in ADS, where we typically impose some sort of reflective boundary condition, and we say that we put gravity in ADS, CFT, we put gravity in the box, but here rather you are dealing with a very different situation. So given these differences and difficulties compared to the usual ADS CFT case, you might wonder where should I start from, and the point of view I want to advocate in this presentation is to follow symmetries. So the very first question, which is really the question level 0, if you want to start with such a holographic description, is what are the symmetries at the boundary of flat spacetime? And now, rather famously, the answer to this question was given, partially at least, in the works of people experts in general relativity and gravitational waves, Bondy, Messner, and Sachs. And what they found is what is now called the BMS group, which is an infinite extension of the Poincaré group. So the asymptotic symmetry algebra of flat spacetime is way richer than you might have imagined naively, as you get an infinite dimensional symmetry group rather than the pure isometry group of Minkowski space. So these BMS symmetries enhance the 4 usual translations of the Poincaré group to an infinite amount of what is called super translations. So these super translations are generated by the symmetry parameter. So they are super because it has nothing to do with supersymmetry. It's super because you have an infinite amount of translation. One translation for each point at the sphere at infinity, which is called the celestial sphere. So originally, these symmetries were totally disregarded by not only the GR community, but much more broadly, until it was realized much later. Most of that was realized by Andy Strominger and collaborators, that these symmetries actually constrain the gravitational S matrix. So you have to imagine that you set up a gravitational scattering process where you have incoming particles coming from scribe minus or I minus, interacting and going out at scribe plus and I plus, time like in future infinities. These symmetries give a constraint on any scattering process happening in asymptotic flat spacetime, and so any dual theory should be consistent with these symmetries. Moreover, they have nice, beautiful observables associated with them. They are the so-called memory effects in gravitational wave. And finally, the symmetries found by Bondy and collaborators are only a part of the answer, as we now understand that they allow further extensions so as to allow not only the Lorentz group, but a local enhancement of it, namely the full conformal group or the Virasoro symmetries. So all these rather recent observations are what have led to a sort of revival of flat space holography, and the hope that thanks to the understanding of these points, we could actually make progress in this question. Okay, is there any questions at this stage or comments? So, a very first question you can also ask is, where the dual theory should live. What is the proper asymptotic boundary that you have to consider? And this has led to two sort of proposals, let's say, for flat space holography. The first natural boundary, okay, I mean, if you care about massless particles, I will have some comment about the massive case, but if you care about massless particles, a natural boundary to look at is null infinity, which is a light-like surface given by a real line spanned by this retarded time mu that you've seen before times a two-sphere. So then you would be looking for some symmetry living on this null boundary which enjoys these BMS symmetries. Or you could think of the dual theory living on the celestial sphere, and that's what people call putative dual celestial CFT. So these two choices, if you wish, of boundaries have led to two different proposals or ways of addressing the problem, and they run under the name of Kaolian and celestial holography, and I will talk about that more in the next slides. So that's precisely the outlines. I will try to review what are the main features of celestial and Kaolian holography, and then I will try to explain what some interesting new symmetries that have emerged in both contexts, and I will make some final remarks. Okay. So let me also say that this is a review talk, which is not meant to be, of course, an exhaustive survey on flat space holography. It's focused on my personal taste and expertise. So if you have, it might be not the only way to address this problem. So I encourage you to look at your what you think are the best options and the more efficient ways to do it. And it will also be a selected subpart of all these topics, as of course I will not have time to cover our recent advances. Okay, so what is celestial holography? So if you're a student or a young researcher and you're interested in that and you want to learn about this, I'm listing here a bunch of review and lecture notes on those topics. I think the building blocks of all this is in this a book by Strominger, published some time ago now. And then on celestial holography itself, there's been some recent, a bunch of reviews from different perspectives. These are more on the amplitude side. And the review I wrote recently was more on the asymptotic symmetry perspective. Okay, so what is celestial holography can be stated as a sort of conjecture that four-dimensional S matrix can be recast as in terms of a two-dimensional conformal field theory or exotic sort of conformal field theory that we'll call celestial CFT living on the celestial sphere. So for massless particle, what you will do is, you will describe your massless particle as usual with a null momentum P mu, which is labeled by an energy and a point, Z at Z bar, at which it perceives the celestial sphere. And you want to rewrite these scattering elements in a way that makes the conformal symmetries as manifest as possible. The hope being that if you have something looking like a 2D CFT, you can apply the very powerful techniques of 2D CFT to try to understand this dual theory. So how do you make this conformal property manifest? Well, you work in you recast these scattering amplitudes in a different base. How do you do this? Well, you perform, instead of working with your usual momentum basis, where you have your plane wave packets e to the iap.x, x being a point in the bulk, then you perform this integral transform. It's called a Mellin transform. And basically what it does for you is that this Mellin transform trades the energy of your massless particle for a new number, which is called delta here. And this delta precisely plays the role of a conformal dimension in a CFT. As you can see that now your new what is called a conformal primary wave function here on the left-hand side, thanks to this Mellin transform manifestly as some quasi-primary of weights h and h bar, or if you wish, the sum being denoted by big delta. Okay, so this is just, instead of using the momentum basis, you work in different bases and you exhibit some SL2C transformation properties in a manifest way. So that's very simple. And so if you wish, by definition of biconstruction, if you start with the scattering amplitude and apply as many Mellin transform as you have as external particles in your amplitude, then by definition you will end up with something on the right-hand side which transforms nicely under the conformal group. And you call this a celestial amplitude or a celestial correlator. And you want to see what are the properties of this right-hand side and to which extent you can actually call this a 2D CFT or not. And many celestial amplitudes have been computed in the recent years. So there was a time where I could list all the authors and all the references, but now this time is gone. So I'm just not listing anyone for now. But you can find many references, all the references in the reviews that I have mentioned before. And notice that you have an analogous, well, mutatis mutandis map for massive particle as well. Then we will focus on massive scales. So some features about these celestial amplitudes. One feature is that is a very simple kinematic fact that a collinear limit in the bulk corresponds to taking Z1 and Z2 to be very, very close. So in this way, you can extract operator product expansion in the right-hand side. So it has been used a lot. As is apparent from their definition, these amplitudes involve integral over all energies. So you have a sort of UV-IR mixing. And this leads to amplitudes which are usually divergent, sometimes ill-defined. Most of the, well, sometimes, if you're lucky, there are distributional amplitudes, and you can try to make sense of them in that way. So that's an issue that sometimes people want to circumvent. So I'm just listing some ways that you can circumvent, and some of them will be addressed in talks during this conference. So you can work in string theory, which will leave you some better UV behavior. It's also interesting to see what happens when you turn a background field. There will be some talk about that. And also it has been pointed out that maybe working in iconial approximation, it's also a better idea to have better defined amplitudes, celestial amplitudes. So the thing I want to focus about is the universal aspects of these amplitudes, which are well defined and which are expected to hold in general. And this universal behavior I will be focusing on has to do with the symmetry algebra, and this will be the focus on my talk. So this new universal behavior of celestial amplitude brings us to the so-called celestial currents, which arise in the so-called soft sector of celestial CFT. So we know since the work of Weinberg in the 60s that you have a universal factorization properties for amplitudes, where you take one of the external, say, graviton or gluons to be soft, you take its energy to 0, then your amplitude with the n particle plus the soft one, will factorize and will be given by a number times the amplitude without this soft particle. So this Weinberg works out the leading soft theorem, but there is also a subleading and a bunch of more subleading theorems that I will mention later. So it's an interesting thing to do to look at the analog of what is this soft limit in these new bases, these conformal bases that I mentioned before. And when you do so, you find the existence of a current in the celestial sphere which encodes, if you wish, this soft factorization and properties. So for the leading soft graviton theorem, it's understood that now it can be equivalently understood as some Ward identity associated to these BMS symmetries I was mentioning in the beginning, the supertranslation symmetry. And you have a 2D current living on the celestial sphere encoding the supertranslation. It's called a supertranslation current. It satisfies this kind of OP with, so O here denotes any operators on the celestial sphere obtained from this Mellin transform I was mentioning before. And you can see that this is sort of weird Catch-Moody current. It has weight when the conformal dimension 1, but it also shifts the weights of the celestial operator by a half. It has this funny weight, a half primary. But so it's something that, for instance, you are not very used to seeing in a regular CFT, but is there because of the presence of supertranslation symmetry. Also, very interestingly, if you look at the subleading structure, so subleading in the energy, then the subleading soft theorem, found later by Kachazo and Strominger, is also in one-to-one with the wide identity of this super rotation of Virasoro symmetry generated by this local normorphic vector field Y here. And very interestingly, you have a stress tensor, so the current associated with this symmetry really behaves like a stress tensor of the usual CFT. It's a 2-0 primary, which in fact arises from the so-called shadow transform of a delta equals 0 mode. Not entering into all details here. But you have some sort of this, you can show from the amplitude sides, for instance, you can take some scattering amplitudes, insert this operator. How you do that? Remember, you take Mellin transform, and then you take this shadow transform, you take this limit, delta goes to 0, and you can prove this kind of OP for a stress tensor in celestial CFT. So it's very promising because it promotes the celestial operator from quasi-primary to full Virasoro primaries. And there, in fact, there is a bunch of more subleading structure that I will mention later on. Okay, so that's basically all I'm going to say about generic features of celestial holography. So many things are not understood. For instance, we don't really understand what this theory is and what is the spectrum, how to organize the spectrum of this theory. It's not expected to be a unitary theory. But exactly what are the properties is still an open question. So we are very far from being able to write this kind of book. Okay, so I will turn to Corellian holography now. Is there any comments? Question? Yes, thank you. Well, first, so it's a feature there. So the question is why we expect the theory to be non-unitary. So there are many hints from what we found when working out the celestial amplitudes. So, for instance, you have, I talked about this stress tensor. So you might wonder, can I compute the central charge of this stress tensor? And you find 0, at least in very approximation. So you think, okay, so if it's a unitary CFT, it will be very trivial. So that's one hint, for instance. Also, there are other arguments. We rely on the fact that somehow you have, because of these leaks of radiation escaping the boundary, there is really no reason to explain that. Okay. Yes, at the back.
So there's recent work on CCFE being in a certain region, like celestial conformation realized on CFE at windows of global time within the areas. So does this add to insights on the unitary properties of CFE?
So can you explain better which work are you referring to? Yeah, okay. So all this, yeah. So I think all this is some works which are aiming to try to understand celestial amplitude from some flat space limit of ADS. So there's been many recent works on that. I will not touch much upon that. I think it will be the object of several talks in this conference. But yes, so basically there has been recent attempts. Of course, it's a natural question whether you can see this as arising from some flat space limit of ADS correlation function.
In that case, this leaking radiation, right? If you take the flat space limit of ADS, you still have a boundary, right?
You split the boundary?
No, you still have a boundary, right? So let's take ADS, it has a boundary. You take the flat space limit, you still have a boundary. And in that case, is there radiation leaking out of the space? Because I understand that makes a
exactly.
difference.
So if you wish basically to encode these leaks from a flat limit, you also have to allow for leaks of radiation in ADS as well. So relax the usual assumptions. Otherwise, what you will find is a boring story in flat scales. You will not find any super translation, any sort of gravitational. So yeah, that's the complication. Somehow you have to relax many of the assumptions that you're used to have in ADS. Okay. Great. Thanks a lot for the interruptions. Good. Okay, so let's turn to Carolian holography. So if you remember now, the theory is not supposed to live on the celestial sphere, but rather on the full null infinity. So what is this name comes about? So I have to tell again the story. So this Carolian group arose as some curiosity by some French guy in the 60s, where he thought, okay, what if instead of taking the c goes to the speed of light to infinity limit of Poincaré, where I obtain the usual Galilean spacetime, I take the opposite limit, I take c to 0. And then he found some group that he called the Carol group. Why? Because in the Carolian spacetime, the notion of time is totally arbitrary, and space-like separation are space in absolute and time intervals are totally arbitrary. And he reminded him of this story in Alice in Wonderland, where Alice is having this, for instance, this tea mat party, where it seems that there is no causality whatsoever in this kind of space-time. And it seems that people like a lot this Carol name, so it sticked. And now, it sticked around. And let me say that I will talk about Carolian spacetime, Carolian geometries, and physics from having in mind holographic application, but it has much broader application, and it has gathered several people working at the forefront of different topics, especially black hole physics or a fluid gravity correspondence. So Carolian physics are interesting beyond flat space holography. So what it has to do with the flat spacetime? Well, it's just an isometry fact that Duval, Gibbons, and Horvath showed, is that if you extend this Carol symmetry to the conformal Carolian symmetries, that they're basically isomorphic to the BMS symmetries. So in particular, one way to rephrase is that there are conformal symmetry of so-called Carolian structure, Carlin structure involves a degenerate metric and a vector field living in the kernel of this metric. So for null infinity, this is just what this degenerate metric is this one. And if you look for the conformal symmetries preserving this Carlin structure, what you find is this kind of vector fields. And if you're familiar with this BMS symmetry, you immediately recognize as BMS symmetry vector fields. And so that's what I was mentioning before, that this is the conformal Carl group in D dimension is isomorphic to the BMS group is one higher dimension. Okay, so BMS field invariant, conformal Carlin invariants are the same things. So now, if you take this sort of proposal seriously, you can play somehow the same game as you did in celestial holography, and you can try to see or to interpret S matrix elements as some correlation function of the field theory living at null infinity, conformal Carolian field theory, and see how far you can go. And this is what we started attempting to do in this paper. So the game is you want to express your S matrix element as some correlation function of this Carolian field theory. So now the new feature is that these fields here, they depend not only on Z and Z bar, but also on the retarded time. And how do you get these guys where you can obtain it from the bulk field by doing a large R expansion? So the S is the spin of your particle, and then depending on the spin, you have different asymptotic behavior. But you can extract these. You can extract the Carolian fields. They will have some what we call Carolian weights, K and K bar. So if you wish, this is a sort of generalization of the usual transformation for a primary of certain weights. But now what we call Carolian weights is consistent with the transformation rule of this boundary field, this field at null infinity under these symmetries. So now that you notice that you have on top of the usual Z and Z bar and the usual Virasoro transformation rules, you have these P's involving the retarded time. Okay, so you can basically do this map and see what you can say on the correlation functions. As you can imagine, there are a lot of pathologies. I will comment on some in a minute. But let me first mention a few words about Carolian theories. So I want to emphasize first that people often say that Carolian structure arises from null hypersurfaces, but it's not only the case. There is actually a very rich story arising as well at time-like and spatial infinity. You have also some Carolian structures over there, and it's very important because if we want to describe a generic scattering process, we also should be able to describe massive particles. So Carolian physics can do this. And I also want to mention a few recent works on Carolian field theory from an intrinsic perspective. Some people have been trying to say, okay, let's start from scratch and try to see what are the main features of a Carolian field theory. And as I was mentioning before, you have some sort of pathological behavior or weird behaviors. So the spectrum seems to exhibit some degeneracy. You have non-normalizable ground states. It has been argued that some of these a priori features could be regulated when you work on the lattice. It's a recent paper by these authors here. So, I mean, of course, by now I'm not able to tell you what exactly is a quantum conformal Carolian field theory. But it's an interesting thing to basically look at this theory from an intrinsic perspective and see how far you can go in their definition. And always it forces you to question and to revisit the usual assumptions and the usual story that you are used to. So it's an interesting thing to do. Okay, so there will be some more talks about Caroline field theory in this workshop. So I encourage you to listen and talk to these people. Now, you might wonder, okay, so what is how the Corellian and the celestial picture talk to each other? Well, all this is supposed to be equivalent, so there is a simple way to go from Corellian operators to celestial operators. So the map is quite simple. So this is how you obtain the celestial operators, labeled only by this conformal dimension, the spin, z and z bar, from these conformal primaries here. So basically you do a sort of light ray transform on this Corellian object. So in other words, all I've been telling you about is the fact that you have, in flat space, you have an S matrix. If you do a Mellin transform, this is a summary. If you do a Mellin transform, you go in the celestial basis and you get celestial amplitudes. If you now go to position base, you do a Fourier transform, you go to a Corellian basis, and of course you can close the loop by combining this transform. This is how these things relate to. So there is nothing very mysterious about that. So at this stage, you might ask about these questions, which are a very relevant question. So I will hopefully answer one of them. So just change the basis. Yes. Is this holography? Not really. Is this useful? I think yes. So can we learn something? I think yes, and this is what I want to turn to now. I want to present something something new that was not realized before addressing before having this point of view. Okay, so this brings me to these so-called LW symmetries. I think I'm doing bad on time, but I'm sort of incorporating the questions during the talk. Is it okay? So then you can ask questions if you want about Corellian or anything before I turn to the symmetries. Okay. Yeah.
So these Carolean field theories, are they local quantum field theories?
It depends really what you mean by that.
Are they UV infinities local?
Sorry?
Are they UV infinities local? The divergences, are they local?
I don't think it's understood. Yeah. If someone has comments on it.
Slightly related question, like, do these Carolean field theories, are they unitary? Do we know something about that?
So you see, when you talk about unitary, you have to say more. I mean, you have to define some. We are not even at the stage where we can actually properly, say what is what are the condition, what is the Hilbert, like we are not at this level there. So unitary in which we have to.
And do you think we can have some relation between the non-unitarity of celestial holography and the Carroll structure?
Yeah, so absolutely. So I think any feature, that's why these two perspectives are interesting to pursue in parallel, because sometimes one question is very murky in one language, and when you turn in the Corellian picture, it's very simple, and the other way around. Like natural question you can ask in CFT language, on the other hand, are obscure in the Corellian framework, but when you talk about fluxes charges, a lot of people in GR have understood many things in this perspective. So that's why I think it's very promising to relay those, and the questions about unitarity, spectrum, and all that. It's probably useful to always keep an eye on both and then try to see, okay, but this I understand in this way, and let's see how I translate in the other way around. I think that's promising.
I know you are avoiding talking about massive scattering, but do we know where exactly these are encoded, like from a holography perspective? Like, is it at
In
I plus
celestial...
in Carolian or in Carolian picture?
In the Carolian picture? Yeah, so in the for the case of massive particles, you have also a Carolian structure. It's called what people call tie somehow. I refer to Kevin is worked on that, for instance. So there is also a rich structure over there. So the map is a little bit more obvious in a sense, like, okay, it's related to this hyperbolic foliation around the time like infinity, and you can see the map easily in this case. So we can talk more if you wish. I can give more detail. All right. Good. So let's see how I can wrap this up. Okay, so but let me turn to these what I think are new symmetries and what we learned. What is new that we learned from this perspective? So if you remember some slides ago, I told you that you have if you take this conformally soft limit, so you take this dimension to go to, I show you the super translation current when you take delta equal to 1, and then I told you there is a stress tensor when delta equal to 2. You have currents on the celestial sphere, and in fact you have an infinite amount of such currents, one for each values of negative integers for this conformal dimension delta. And this will be useful for the following. So this is the form of OPE, a celestial for two gravitons. So this is the helicity. They are both plus 2 helicity. So OPE up to graviton. This has been computed in this reference. So this is just a closed, really simple form. This is the Euler beta function. Then you have some descendants here acting on this celestial operator over here. So you have an explicit form. So if you remember, to get the OP, you have to take this collinear limit in the bulk to get these sort of things. And you can rewrite this graviton OP in terms of these modes here. So if you wish, this graviton OP implies this sort of algebra for the modes here. So these are the holomorphic modes of these celestial currents over there. And this OP can be seen to be equivalent to this algebra formed by these holomorphic modes here. And as you can see, it's very nice because it's closed algebra, but it's rather complicated. You have all this bunch of terms here. And what Strominger realized, sort of very nice way, is that if you redefine this generator here in the following way, so instead of working with the H and K, you work with these W generators here, which are related to the blue things in this way. Then using this redefinition, the complicated bracket I showed you before simplify to form this algebra. So let me note that the label here, P, runs from 1, 3/2, 2, 5/2, and so on. And each value, so for instance, the 3/2 value corresponds to the generator of super translations. The P equal to 2 corresponds to the generator of super rotations of Virasoro. But you see you have an infinite tower of such symmetries. And this little m index here is required to is restricted to this value. It's called the wedge algebra. And this algebra is known from other contexts, is the so-called wedge algebra. Well, is the loop algebra of the wedge algebra of W1 plus infinity. And so what Strominger found is that this infinite tower of soft theorem somehow in the bulk is totally encapsulated by a single algebra, which is this LW1 plus infinity algebra. Okay? Is there any question on that? I'm being a bit fast, but that's what it is about. Okay? So just to reinstate, here you have a bunch of generator, and the value of the P labels each a transformation, an asymptotic, well, if you wish, a sort of symmetry generators from the bulk. And these arise from this infinite tower of tree-level soft theorems. So now the question you might ask is, very well, so I have this infinite tower of celestial current, which is organized in terms of this algebra. But a very pragmatic question you can ask is, how does this algebra act on the Carolean field, or just on any very simple field you might have in the boundary? And to answer this question, well, it's very natural to go to twistor space, as some people here in the audience explained to us that, in fact, this LW1 plus infinity algebra has a very natural implementation in twistor space, known for a long time to be around. As in fact, in the twistor, well, it's very complicated to see. You see, it's very complicated to see from this celestial perspective. You had to figure out this redefinition of generator is very obscure. You would not have guessed it, but from the twistor space point of view, this algebra is just some algebra arising because of you preserve some Poisson structure. So this is very simple. So I'm going to be very fast on that, so I'm not going to explain the details. If you want, you can check out the references. But these are the G's will be the generator of the algebra, and you have this very simple Poisson structure. Yes?
So you were speaking about this infinite soft theorem which relates to W1 plus infinity, but there is no really infinite soft theorem because after sub-subleading order, things don't factorize. Only a partial part of the amplitudes which factorizes and fixed by some gauge invariance, but there is still a non-factorized parts left, like from sub-subleading order onwards. So what is the soft infinite order soft theorems you are relating to this W1 plus infinity algebra?
Yes, I'm referring to this Amada and Shu paper.
But there is it's not fully factorized, right? After using some projection operator, only a part which is fixed by gauge invariance factorizes. But there is no real infinite order soft theorem, because if there is, then I can desum in all omega and I can have the full amplitude. I don't need quantum gravity. For example, I can scatter 2 electrons to 2 electrons, resum, I can have a waveform for this process, all orders, in all omega.
Yeah, so it's a sector. Of course, it's a sector where you have these infinite towers. Yeah, and on the gravity side, it's also related to self-dual space. I'm not saying that all this is the full symmetry of the S matrix. Of course, yeah, of course, because by this Penrose construction, that it would mean that the theory of gravity is integrable, for instance. So of course, then I think it's the analogous statement what you're saying, that you can solve everything. So.
Okay.
Thanks for.
Only the projected part of the theorem after from the algebra, right?
Yeah, the part that does the factorization. Yeah. Thank you.
Yeah.
In
that case, all these powers of theorem came just from residual symmetry of some gauge, right? Like the Lorentz gauge in electromagnetism, or the Donder gauge in. So it's a bit surprising, right? That an abelian theory from the bulk gives all this algebra. I mean, it's a very naive comment, but residual symmetries of Lorentz gauge are just. They commute with each other, of course, because it's an abelian theory. I don't know if you have any comment about that.
No, not true. You mean that this infinite tower, Amada and Shu, can be just understood from the? I'm not really sure it's actually just coming from the the Lorentz. I mean, we should talk. I don't think it's a big idea. Okay, thanks a lot for. Oh my God. Okay. That was okay. That was my fault. I wanted to leave the room for. Anyway, it's better. I mean, it's better. I cover less, and then we have questions because this was an important comment. Thank you. So yeah, I mean, these symmetries, of course, corresponds to a subsector of the symmetries of the full quantum S matrix. That's for sure. But let's be very pragmatic and see how this algebra acts on the Carolean fields. I will try to be quick on that. So I already told you go from the bulk, you just do a larger expansion. You can go backwards for the Kirchhoff-Dademar, but it doesn't matter so much. And then what Penrose is also telling you is how to go from, well, by doing the Penrose transform, you can associate a twistor representative, which is an element of this cohomology group. And there is a one-to-one correspondence between a twistor representative and what he called a zero-rational fields of helicity S in the bulk. So it's just a linearized solution to the equation of motion in the bulk. But so you see there is a way to get a twistor, a representative of this thing very naturally. And so the question is that imagine you have a field as cry, so the typical data you have is the gravitational shear at null infinity. So it depends on u, z bar, or lambda here, the point of the celestial sphere. And I act on it with this LW1 says infinity. How does it look like? How are these symmetries acting on these fields? It's a very naive question. We know that it should act in a way. I mean, Adamo, Mays, and Sharma told us this explicitly. We wanted to see the formula appearing. So the way you do this is you go to twistor space, as I was mentioning. So you have the path that we follow in this reference with Yannick Herfra and Laurent Fredel is to start with the field at scry, you uplift it in twistor space, you get a twistor representative, and once you have twistor space, life is easy with these LW symmetries because they just act with this Poisson structure over there. But the complicated thing is to get back to scry. So the way the path that we followed is to perform a Penrose transform that brings us, so delta H is the twistor representing your field at scry. Once you have acting upon by these LW1 symmetries, okay, you have this object, it's easy to compute. And then to go back in the bulk, you do a Penrose transform, and then finally you make a larger expansion to finally obtain the shear after you have acted with these infinite towers of symmetries. And what you get is the following very, very simple expression after all. So here, this is the shear of helicity plus and minus. So here, you know, everything is in principle is complexified, so they are not complex conjugated of each other. So, so these are your LW1 symmetry generator, with now I'm labeling N. So remember before I had the little p that was 3-half, 2, 5-half. Now it's recast into this little n here. So you have your infinite tower of generators. And you see that the action on the shear, on the Carolean field, if you wish, the stuff living at scry, is, so here is the linear field at scry. So here what you see is that on the z and z bar coordinates, it's very easy. So just, you take d, z bar, there's respective with z and z bar, or z bar here. But you see that there is a very non-local implementation of the symmetries from the point of view of your conformal boundary, because you have this bunch of integrals over U here. And that really shows how this symmetry acts in a non-local way in a twistor space. But this is an explicit expression, which also match with other analyses done previously from a different perspective. Okay, so the summary, I'm just wrapping up, promise. So these LW1 symmetries are, I think, new ingredients in this flat space holography program. They arise as organizing the subsector of celestial CFT, and from the Corellian perspective, you can also see exactly how they act upon. All right. And okay, Bin will talk about, I think today, about some deformation of the symmetry for non-Valentin cosmological constant. And I think that I will not have time to say much about my final comments. But what a very open question is: what is the fate of the symmetry beyond 3 levels? How are they corrected? I mean, there were mentioned the fact that they are not expected to be symmetries of a full quantum S matrix, but a subsector of it, at least organizing a self-dual sector. And this is still an open question. So I think I'm just going to skip that. I wanted to make a comment about this loop, this log correction to sub-theorems that were recently uncovered by some of the people here, Stan and collaborators, and see how you can obtain them from some symmetry principle. But there will be some talk today. I encourage you about Shreya Chagrawal, who worked on this with me, and who will explain to you how you can get this log correction. If you're an expert on that, you just can come to talk to me. I will not have time to say more, unfortunately. I'm just skipping over. So let me finish by trying to wrap up and summarize. So I've been trying to tell you that it's a sort of nice idea to see how to describe quantum gravity in flat space in terms of either celestial field theory living on the celestial sphere, or a conformal Corellian field theory at Scry. So there are kind of two perspectives. Of course, as I was alluding to, it's not really, of course, now a fully fledged description of flat space holography. It's just the beginning. We are trying to establish at least the very basic constraint that any dual theory has to satisfy. They have to come up with some dual. They have to be consistent with these symmetries in a way or another. But of course, we want to go beyond that and arrive some top-down constructions. There has been some recent developments on that in the twisted holography program. Costello and Paquette and others have some sort of top-down construction. And I'm listing here a bunch of open questions and you can hear about recent progress in some of these topics in the rest of the conference. So hopefully they will say more about this. And finally, let me close by showing you that, re-emphasizing that these BMS symmetries are expected to be observed soon from gravitational wave experiments at LIGO or LISA. So this is the displacement memory effects, which imprints the existence of BMS supertranslation symmetries. So it's very nice to make contact with observation. And we also say that, I mentioned different asymptotic symmetry groups and all that. There's been different proposals in the literature for what is this biggest or the biggest symmetry group of asymptotically flat spacetime. But gravitational wave experiments are a way that we could use to discriminate and between different proposals. So I think it's very interesting to continue dialogue with the community on that. I think it's very important. So I think I'm done. As we have seen, what these topics brought us into different soft field. We had to deal with quantum field theory, conformal field theory, but also I think it raises very deep question in general. So beyond if you want, the goal of having a holographic description, if you're studying this question, it makes you pose very deep question about, scattering problem in flat space-time. We know it's not well defined. We have infrared divergences. These BMS symmetries are new ways of understanding these infrared divergences. We also have to deal with very deep question, an important question about gravitational waves. Twister, which brought us back to twister theory, which was somehow the very first origin of the spirit of celestial holography. And also, we have many interesting interplays between all these fields and people working in mathematical GR, people working in stability theorem, peeling properties, and so on. And also, I think with the gravitational wave observation, as I mentioned. So I think I'm really over time, so I will stop. Thank you very much.
Okay, so we had many questions, but maybe a couple. Yeah, David?
Yeah, I have a question. I know that this is under construction, but I have a question about whether there are any ideas about how the parameters in the putative quantum gravity theory in flat space would match to parameters in the CFT. In particular, for example, the Planck length or the string length, if you imagine it's some string theory. Do you have any ideas about how those would map to the CFT? Because in the case of ADS, the reason it works is because you can compare with the ADS scale and get dimensionless ratios. But in flat space, you don't have that scale.
Yeah, no, we don't have that scale exactly. So that was also one of the reasons why somehow you have, zero central char and all that. So we don't have, we are not at the stage where we have a precise map. There are many ways of understanding somehow. There are some ways in which you can understand an immersion of the scale. It's related to this infrared cutoff and all that. But we don't have, a map where we can say, okay, this parameter in the theory and this one is the dual. Because we are really lacking some concrete toy model example of any celestial field theory. That's really what we should aim for.
Yeah.
I have a question about the use of the word holography, because holography refers to a reduction in the number of degrees of freedom, which is not at all visible in any of this, because we are mostly constructing S-matrix elements. My question is, what would be a holographic success of this story? So, for example, thermal flat space presumably does not exist. So, like we do in ADS-CFT, we compute a partition function, and we see it scales with the area, not the volume, and so on. That's holographic. That clearly cannot be applied here. But what would be the type of thing that you could possibly compute that would tell you that this is in fact a holographic correspondence? For example, if you do very high energy scattering in flat space, then you imagine that black holes will form. This makes the amplitudes very soft and so on. You could imagine that this would be a feature that is kind of holographic. Is that something that would follow from the boundary structure, or do you have any other suggestions how we would what we would need to do in order to claim that we're doing something holographic rather than kinematical?
Yeah, I think this is a very deep, question, and I think the hard thing is actually to ask this question and to look what is feasible to answer. Of course, at the end of the day, we'd like to understand. For instance, is there a notion in which we can see black holes from this finite temperature of this celestial CMP and compute something from there? But we are not there yet.
But these boundary theories, do they give you any information on high energy scattering? A priori, like do all these symmetries and so on, do they tell you anything about the properties of high energy scattering in flat space, where you would imagine that black holes are formed as some intermediate unstable state or something like that?
Well, so yeah, these symmetries, of course, is a certain sector that has the advantage of being, universal, but we need more than this symmetry. I mean, they will not, I believe, probably they will not tell you about that, and you have to do more, maybe working in the iconal, look at the iconal amplitudes and so on, and do more than that.
Thanks.
Yeah.
Okay, I think we can move. Oh, there's one question there. This is the last one, I guess.
So another infinite dimensional symmetry group in gravity is the Garoff group. So this is for spacetimes which are stationary and axisymmetric, so like the Kara black hole, for example. And I was just wondering if any of the new tools or things we're learning about the BMS group in this context have been applied or could be applied to learn more there.
About the Garoff group?
Yeah, or applications to things like Kara spacetime that are described by that infinite dimensional symmetry.
I'm not aware of that, so yeah, I have never read something along those lines. But if there are some other experts that can comment on that, and we can talk more just exactly to be sure we're talking about the same thing.
Okay, so let's thank Laura for the very nice review.